In this video lecture, we're going to look at the optics of the eye, or how the light gets focused on the retina. To do this, we're going to first look at the properties of light and just differentiate between convex and concave lenses. And then we'll describe how the light focuses, or excuse me, how the eye focuses light on the retina and using a methodology called accommodation. And then we'll look at the different disorders such as presbyopia, myopia, hyperopia, and astigmatisms. First, looking at the properties of light. Visible light is part of the electromagnetic radiation or spectrum. The wavelengths for visible light are between 400 and 700 nanometers, which we see here, just this small range of the entire electromagnetic radiation. The purple end or violet end has short wavelengths, whereas the red end has very long wavelengths. And then, of course, it's a continuum in between, green having about medium. You can see the differences, the different colors, and their wavelengths over here. Now, that property will come important later when we talk about how we do see color. A couple properties of light. First of all is refraction. Refraction refers to light being blocked by a non-transparent object and then bouncing off of its surface. So you can see here light's refracted off of this surface, and we have gorgeous pictures of lakes with the water reflecting off the surface and giving us a mirror image. Refraction is a bending of light when it passes from one transparent medium to another, and we see this here where the light going through air has one direction and then it's bent when it enters a different medium. Okay, or actually I should say when it cuts, this here would have to come through the water first and then the air before it reached our eye, so it looks bent. And that's what we see with the spoon, that a spoon ends up being bent. Here the part of the handle, part of the spoon only passes through air to reach our eye, but this portion that's in the water has to go through the water and then the air passing from one transparent medium to the other before it reaches the eye. And so it makes it bend it and makes it appear that it's not linked up to the handle of the spoon. To focus light on the retina, we're going to use refraction to bend the light. And so when the light passes through one medium, it's going to bend. And so it passes through air, then it's going to pass through the cornea. That's going to cause it to bend. It's going to pass through the entrance of the lens, which will cause it to bend. Another area leaving the lens will cause it to bend. And then finally it hits the retina. Now the aqueous and vitreous humor will also cause it to bend, but not any worth mentioning really. So really it's just the cornea and the lens that bend the light in order for that image to focus in on the retina. But we can only adjust the amount of refraction, or how much that light bends, using the lens. This portion, we can make this lens thicker or thinner to bend the light more or less. The cornea is fixed. You can't change its thickness in order to bend the light more or less. Okay? So let's first look at the two types of lenses before we get into how the retina, or how the lens actually gets light focused in on the retina. The first one is that convex lenses. Convex lenses converge light as it passes through that lens. And it converges it to a single point called a focal point. Now, a thick lens causes refraction more there, and therefore you have a shorter focal point, and you can see that here. We have a thicker lens. It's going to make the lens bend more, and therefore our focal point, that is how far it is from the lens, is closer or shorter. A thin lens here is going to bend the light less, so the focal point ends up being farther out, so you have a longer focal point. Okay, now because of the way the light is bent, it actually will flip the image upside down, and you end up with an image in the back of your head, or in the back of your eye, that's upside down from what you see. But your brain deals with that and reverses that image in your head. A concave lens diverges light out. So our lenses of the eye will not use a concave lens because that obviously doesn't focus anything. The focal point is actually in front of the lens, and that's a lot of physics to do with that, and we're not going to worry about that now. But just get the idea that a concave lens isn't particularly going to be helpful in focusing light for our eyeball. However, you'll see where we are going to use concave lenses in order to fix particular disorders with our glasses. Now, if changing the thickness of the lens changes the amount of refraction, then how do we change that thickness? Well, that has to do with the ciliary muscles and the suspensory ligaments around it. So first of all, let's look to make the lens fatter. Now get oriented here. Here's these ciliary muscles, there's the suspensory ligaments, and then here's the lens. I like to think of this as kind of like a trampoline, with the ciliary muscles being the frame of the trampoline. The suspensory ligaments are those coils along it, and then of course the lens is the surface of the trampoline that you jump on. So if I could adjust the frame size of my trampoline, you can imagine if I made my frame smaller, that it shrunk in, that would reduce the tension on the suspensory ligaments as well as on the lens or on the surface of our trampoline, and would make the lens really fat. Okay, and that's what happens to make that lens fat. Those ciliary muscles are going to contract. When a ciliary muscle that's arranged in a circle contract, it makes the circle smaller. Because remember, every single muscle has to contract, and that shortens that muscle. So the ciliary muscle actually becomes smaller in diameter, relieving the tension on the suspensory ligaments and therefore making the lens fat. To make the lens thinner, then, we relax the ciliary muscles. By relaxing the ciliary muscles, the diameter making up the ciliary muscles becomes larger. That puts tension on those suspensory ligaments, pulling on the lens and making the lens thinner. So again, contracting ciliary muscles means the lens gets fatter. Relaxing the ciliary muscles makes the lens thinner. This is going to be an important point for later on to learn how to adjust the lens diameter to focus light. So that's actually where we're going to turn to now. We're going to look first at what's called an emmetropic eye. Now, an emmetropic eye is the perfect eyeball. It's the eyeball that we all should be born with, but many of us who are wearing glasses don't have this eye. But we'll pretend we have an emmetropic eye first. Now, when we look at objects from a distance, the light, for example, this dot, we're looking at this dot from a distance. Now the light, when it comes to our eyeball and hits the cornea, it's really coming in almost parallel rays. You can see here the rays are almost parallel to each other. Since they're parallel to each other, we really don't need to bend the light as much. So the ciliary muscles can be relaxed. That is, the lens is going to be as thin as it can because the ciliary muscles are completely relaxed. That is, our eye is designed this way that when the ciliary muscles are relaxed, it bends the light just the right amount to focus it in on the retina. So the eyeball is just the right size. It's not too long, not too short. It's just right in between. Think Goldilocks, right? Just right. And that way we bend the light just the right amount. Okay? For close vision, and again in our emmetropic eye, were designed to have so that when the light comes in and hits the lens, now notice the light is coming in a diverging pattern because the light's much closer to our eye. That makes it come in in diverging rays. So if it's diverging out, we've got to focus the light in more. That is, we've got to bend the light more since the light's coming in diverging. If we're going to have to bend the light more, we have to make the lens thicker. If we have to make the lens thicker, then we need to contract those ciliary muscles. So anytime you're reading, your ciliary muscles have to contract more, make that lens fatter. That bends the light more so it still focuses on the retina. This idea of contracting the ciliary muscles in order to make them thick is what's called accommodation. Again, accommodation is simply contracting the ciliary muscles to make the lens thick so that we can focus the light. So in other words, anytime we're looking at objects close up to us, where the light's coming in diverging, we have to accommodate. We have to contract the ciliary muscles, make the lens fatter, so the light is bent more and can focus in on the retina. That brings us to two terms called the far point of vision and the near point of vision. First, the far point of vision. The far point of vision is the distance in which no accommodation is needed. So typically when you're looking at distance out 6 meters or 20 feet away, though that distance is so far out that the light's coming into our eye pretty much parallel to each other. Those light rays are parallel to each other. So you really don't have to bend it that much, so we don't need to accommodate. We don't need to contract the ciliary muscles to make it thick. A thin lens is enough to bend the light to focus in on the retina. The near point of vision, however, is the nearest point that we could focus clearly. So in other words, it's how close can you get an object to your eye and still be able to focus on it, see it clearly, okay? This is because as you move, well, think about it this way. As you move the object closer and closer to your eyes, that means those light rays are coming in more and more diverging pattern, okay? So the closer the object is, the more the light is diverging out. So which means we got to bend it even more. So which means then your lens has to get even fatter. So a near point of vision is basically the fattest you can get your lens. And we'll just talk about this more. I'll show you how to find your near point of vision in class. Other ways to help focus on close objects, things that help, is constriction of the pupils. If we constrict the pupils, then you have a more focused light, or you're getting rid of all the divergent light rays that may be entering into the eye and causing problems. And also, of course, convergence of your eyeballs, that is keeping both eyeballs focused on the same object, okay? And you know, as you can do this, as you bring an object like your finger towards your nose and keep your eyes focused on that, you could go cross-eyed. Not permanently, obviously, though, just temporarily. You go cross-eyed. All right, so now let's look at the different disorders. In other words, these are for the people who wear glasses or contacts. The first one is myopia. Myopia is also called nearsightedness. So you think a person who's myopic is nearsighted. Okay, this happens or can happen when the eyeball is actually too long. So we don't have the perfect shaped eyeball. So let's look at the two possibilities here. In a person who's myopic, they have at distances, remember this is nearsightedness, so they see really well close up, they can't see very well far away. So when light comes in at a distance, it's coming in parallel. Remember, the lens is not accommodating, so there's no ciliary muscles aren't contracting. The ciliary muscles are relaxed, so the lens is pretty thin. Well, the light still is being focused too short of the retina. If the lens could get thinner, then it wouldn't bend the light as much and maybe it'd focus in on the retina. But we can't do that because our eyeball is too long, and if the ciliary muscle is relaxed, the lens is as thin as it's going to get anyway, okay? If you look at close objects, if you're myopic, now the light comes in diverging out. So now the lens is the right thickness, even when there's no accommodation. Notice the ciliary muscles aren't contract, so the lens is thin. But because the object or the light's coming in a divergent pattern, the lens bends at the right amount and the light's focusing on the retina. Okay? So person who is myopic can read for hours on end without any accommodation, and their eyes aren't going to tire from those ciliary muscles being contracted because they aren't. There's no accommodation. Now, what do we do to fix myopic vision? Well, we give the person concave shaped lenses. So that way, from a distance, the light comes in parallel, but the glasses diverge the light out. They make the light diverge out, kind of like almost like they were reading up here, but it makes it spread out. So now, without any accommodation, without the ciliary muscles contracting, the lens is thin enough, just the right thinness to focus the light on the retina. Okay? And then when reading with these glasses, the light's going to basically, it's hard to see in this picture, but you have to imagine that the light comes in diverging anyway, and then the concave lens causes it to diverge even more. So now we've got to focus the light by making the lens thick, which means we have to accommodate. We have to cause those ciliary muscles to contract to make the lens thick, and then that will allow the light to focus perfectly on the retina. All right, how about hyperopia? Hyperopia is farsightedness. This often occurs when a person's eyeball is too short. So now a farsighted person or somebody who's hyperopic can see far away, but they can't see close up. So if you look first, the distance objects, again, here's the light coming in parallel. Remember, their eyeball is too short, so they've got to make the lens thicker in order to bend the light on this short focal point caused by their short eyeball. So they can do that by accommodating. That is, they contract the ciliary muscles, make the lens thicker so that it can accommodate and bend the light enough to focus in on the retina. At near objects with light coming in diverging, the lens will try to accommodate. That is, it's going to get as thick as it possibly can, but it just can't get thick enough. So the light ends up focusing behind the retina. So the focal point would be back over here, and that doesn't do any good. It doesn't focus in on the retina, so you can't see close up. To fix this, we're going to use convex lenses. Okay, we're going to help the lens out a little bit. So the light coming in, hitting this convex lens, will cause it to converge a little bit, and now the lens doesn't have to do all the work. The glasses did, that convex lens of the glasses did some of the work for it. So now at a distance, the ciliary muscles don't have to contract to make the lens thick anymore, because again, the glasses helped out, and so there's no accommodation. We get the right focusing on the retina. And when reading happens, then the light coming in diverging is then have convergence with the glasses, as well as accommodation with the lens, making it fat, even more converging, so that means we can get light focusing in on the retina. Okay? Another condition we can have, actually we'll all end up with as we age, is called presbyopia. This is when you start laughing at your parents because they're stretching their arm out full length to try to read something. This happens because of the lens loses its elasticity. A normal eye over here, you know, focuses light in just perfectly with the lens getting nice and fat. This is when we're reading and it focuses in on the retina. But here, a person who's with presbyopia, the lens just can't get fat enough, and so the light focuses behind the retina instead, and so the image ends up blurry. And it just doesn't, their arms just, your parents' arms just don't seem to be ever long enough to get that light not coming in such a diverging pattern. Okay, so they end up with presbyopia. To fix it, we just fix it with some convex lenses, and that way that will help the eyeball, or help the lens converge that light, and then they can see and read. Last disorder we'll look at is what's called astigmatism. Astigmatism is an unequal curvature of the cornea or the lens. Often it's in the cornea. So the cornea should be nice and rounded shape. That is, the arc in every direction of the cornea should be exactly the same. Think of a surface of a basketball, for example. And no matter where you look on the curvature of that basketball, it's the same everywhere. A person with astigmatism, though, doesn't have that equal curvature. Their cornea or lens is shaped more like, say, a football. From end to end of the football, the arc isn't very great, but around the middle of the football, you've got a much stronger arc. So what that does then is it gives multiple focal points on the retina. And so in the old days, I have an astigmatism. I used to go to the doctor's office, and they'd show me this chart. Now the chart actually has lines coming out in the 12 areas around the circle, and all the lines are actually in reality equal thicknesses. What the doctor would ask me is to point out those lines that look thinner, like the 4, 5, the 10, and 11, so because they look thinner. And that would give an indication of where the astigmatism curvature is. And he'd show me multiple ones of these and then mess with the putting, you know, the little glasses in front of you and try to correct for that. Nowadays they don't need to do that because we have computers, and technology allows that to measure the exact curvature of your eyeball, and therefore there's no need to bother looking at those little astigmatism lines. But if you've ever seen one of those, that's what they're for. All right, so that ends our optic unit. The next unit we'll look at then is going to be on photoreceptors and phototransduction. Now that we have the light focused in on the retina, how do we convert those light rays, or the wavelengths of the light, into nerve impulses so that our brain can interpret what we see? All right,